Welcome to the video key for Quiz 0. Number 1, we're riding a bike down a hill. We find the brakes are hot. So why did they get hot? So clearly, if they got hot, it looks like there was an increase in thermal energy of the brakes. So we can say that thermal energy went up, the internal energy went up because the temperature went up. So why? Well, we know that that could be a result of work or heat, either one of those. Now, heat is always a transfer of energy due to a temperature difference. So if we put the brakes in a pot of boiling water, the brakes are cold, the water is hot, so we can have an energy transfer as heat. But here, we didn't let the brakes contact anything hot. The brakes, the wheels, everything was cold until we started riding the bike down the hill. So that must mean that it was energy transfer as work. And if we think about how brakes work, we have the brakes either hitting a disc or hitting the wheels of the bike. In either case, the two surfaces are sliding past each other, so we're going to do frictional work, right? We're exerting a force through a distance. So it was work. Which atom has the smallest radius? Well, here we can see that we can break this into two categories. We've got carbon and nitrogen, which are in row 2 of the periodic table, and here we've got phosphorus and silicon, which are in row 3. So we know that each row represents looking at different shells of the atom. The electrons, the outermost electrons in row 3 are in shell 3, the outermost electrons in row 2 are in shell 2, and each shell, the electrons are on average further from the nucleus. So row 3 is going to be bigger, atoms in row 3 are going to be bigger, all else being equal to atoms in row 2. So now we're comparing between carbon and nitrogen. So let's go ahead and make the periodic table here. I'll just make a little mini periodic table. We've got carbon, nitrogen, silicon, and phosphorus. Okay, so now we're looking at carbon and nitrogen. And as we go from carbon to nitrogen, we're adding an electron and a proton to the atom. And you may remember from 124 that Z effective for nitrogen is therefore going to be bigger than Z effective for carbon. Okay, and if the outermost electron is seeing essentially a bigger positive charge in the nucleus, that's going to contract the atom, and so that means the radius of a nitrogen is going to be less than the radius of a carbon. So the correct answer is B, nitrogen. Which intermolecular forces are present? So we got a beaker of methanol molecules, so I'll draw a couple of methanol molecules. Here's another one. Okay, so we've got a single methyl group and then a hydroxyl group. And we don't normally draw lone pairs on line angle structures. I'm going to go ahead and draw some because then we can draw the hydrogen bonds. Okay, if we have a hydrogen bond donor and a hydrogen bond acceptor between the two molecules, we can make a hydrogen bond. So oxygen, these lone pairs here are going to be the hydrogen bond acceptor. We've got the hydrogen directly attached to an oxygen is going to be a hydrogen bond donor. So we've got at least one hydrogen bond. Of course, we could form another one if we wanted. I'll draw another one over here. We could do this. Okay, so you get the idea. There's multiple hydrogen bonds we could form between methanol molecules. So we definitely have that. We always have London dispersion between any two molecules. To have dipole-dipole, we have to have both molecules be polar. For a dipole-induced dipole, we only need to have at least one of the two be polar. So clearly we have a dipole moment. If I draw this in a sort of a shape structure, we know that this is going to be a bent molecule where we have the hydrogen and the methyl group are going to be at an angle, and the oxygen's more electronegative than hydrogen, so we're going to have a dipole moment like that, sort of in that general direction. And so indeed it is a polar molecule, so we have dipole-induced dipole, and then we have dipole-dipole because they're both polar molecules. You can't have ion dipole unless you have an ion present, and there's no ions present. Okay, so now we've got the stoichiometry heat problem. We're giving a certain amount of water that's produced, and we want to know how much heat was released. So we have the water given, and let's draw a little conceptual map, right? We've got mass of water. We know we can get that. We can get the moles of water, and then we can see, since we have a balanced equation, we've got heat, we've got moles of water. So we can, from that, there's a ratio between moles of water and heat, so we can get Q, and then we're gonna be done, right? So let's do that. So we've got 45 grams of water, and we know that if we have 45 grams, well, there's 18 grams of water for every 1 mole, and so we can cancel that. And then we need a ratio of moles of water to kilojoules, and we can see that here, right? We can see that there's negative 1560 kilojoules for every 3 moles of water. So from that, we can calculate our answer. So we've got 1,300 kilojoules. And notice it's not kilojoules per mole, right? We've taken care of our moles here. So this is not per anything. This is the actual amount of heat that would be given off if we had a reaction where we burned ethane and got 45 grams of water being produced. So 1,300 kilojoules is negative the reaction's giving off heat. All right, thanks for watching.